Hello guys, have you ever struggled to tune PID when you randomly vary parameters but never achieve the desired result? If yes, this video is for you. So after completing this video, you will have intuitive understanding how every gain affects the performance of the system. So next time you will tune PID in a few steps. So in my example, I control the velocity of the motor using PID, but the thing that I want to explain can be used in any PID tuning problem. Also in my project, I set up UART communication, so I can send 3 numbers from the computer, and these 3 numbers will become PID gains. So for example, if I send 1, 2, 3, P gain would be 1, I gain would be 2, and D gain would be 3. But at the end of the video, I will explain how I set up UART communication. So let's right now focus on PID gain, PID itself. Also, I said I have the reference value, which is 60, so I want to achieve this velocity value. So let's resume the code, and when I rotate the motor, I can see the corresponding velocity values in real time. So right now let's send just the zeros. So first we're gonna play with P gain to see how it affects the system. So I send 50, 0, 0. So P gain is 50, the rest gains are 0. So when I send, I got this response. Let's send again zeros. And we can pause the signal, pause the code. So we have this response. So we had 0 value. Then when we set P gain, we have this increase. So it tried to achieve the reference value, which is 60. But the steady, like a final value we got is around 30, even less than 30. So it's really far from the reference value, the value that we want to achieve. Also, we can see this bump. We call it overshoot. When the system overreacts, then it goes down. So we call it overshoot. So what I wanted to do right now is to send 150 instead of 50, and let's see how it affects the system. So we are increasing P gain. So when we send, we get this response. Again, let's send zeros and pause the code. So as you see, the steady state value, like a final value we achieved with this P gain, is around 45, which is higher than we get before. So when we increase P gain, we actually got steady state value closer to the reference value. Also, we increased this overshoot. Also, we have these oscillations. So we can sum up all these results using this illustration. If you're familiar with control systems, I guess you encountered this plot many times. So when you increase P gain, the advantages are first, you decrease this rise time, so your system will react faster, and also you decrease this steady state error, the difference between the reference and the steady state value. However, we have disadvantages as well, because when you increase P gain, you increase the overshoot, this bump. Also, you can make the system unstable. As we notice it, we have some oscillations. So what I want to do, instead of 150, I want to set 200, 0, 0, and run this code, and we can see these oscillations. So let me send zeros again. So when you increase P gain, at some point the system becomes unstable, it will start oscillating. It means that you have to stop increasing P gain. Next, we're gonna play with I gain. So I keep 150. So first let's resume the code. So I keep P gain to 150, but instead of I gain I will set 100, and I keep D gain 0 and run this code. So let me send zeros again, pause the code. So we have a similar response that we get before when we had just a P gain, but at the same time we can see that the output value is slowly converging to the reference value, which is 60. So when you add I gain to your system, you basically eliminate this steady state error. So eventually the output value will converge to the reference value. So let's resume the code and let's increase I gain. So let's set 500, 0, and run this code. So we converge it even faster. So I would say in just a 1 second we reached the reference value, which is not a bad result, I would say. So let's run this code and let's increase further, like let's set 1000, 0, and run this code. We get this response. So we have more overshoot, we have more oscillations, but eventually we got the we reached the reference value. So again, we can sum up all these results. So the main advantage of I gain is that it eliminates the steady state error. So this error would be 0 eventually. You can never achieve it using just the only P gain. P gain can decrease this error, but it cannot eliminate it fully. But using I gain, you can do it. Also, it makes the system robust to external forces, because, for example, if I apply some friction to the motor, it will try to keep this reference value because of this I gain. You cannot achieve it using just the P gain. However, there are some disadvantages. First, it increases this overshoot. It makes the system as stable as we saw from the plots. It starts oscillating. Also, the system might saturate due to I gain, because you are integrating all the time, and this value might become really huge. But there are some physical limitations of any system. I cannot, for example, run this motor with an infinite velocity. It has some physical limitations. So when you set really high I gain, you kind of reaching this threshold, like the physical limitation. So you need to be careful with that. Last but not least, we're gonna play with D gain. So I resume the code. So I keep 150, 500 as P and I gains correspondingly, but for D gain I'm going to set 20, and I run this code. Let me send zeros again just to appreciate what we got. I pause the code. So we have this interesting result, like in less than 500 milliseconds we reached the reference value. We have really small overshoot, as you see, and we don't have any oscillations. So what it means is that when you use D gain, it decreases the rise time, it decreases the overshoot, and it makes the system stable. I really like D gain because it improves the system dramatically. However, you need to be careful with D gain, because D gain is basically taking the derivative of the signal, and for example, imagine that you have like a high frequency noise at 10 kilohertz, and if we take the derivative of this sinusoidal signal, we basically amplifying the magnitude by this value, which is around 60,000 times. So if in your system if there's a small noise in your system at high frequency, you basically amplifying this noise if you're using degain. So due to that amplification of the high frequency components, the system might become unstable, and it might act really in a weird way. We can see it from this system. For example, I keep 150, 500, and instead of 20, if I send 40, I got really weird result. So what I want to do, I just want to send zeros. So you need to be careful with degain. So you basically increase it steadily, and at some point you decrease the overshoot, so you get really nice response. It means that you should stop increasing it. So let's sum up everything. So when tuning PID, we start from P gain, we increase P gain until the system becomes unstable, then we switch to I gain. The main purpose of using I gain is to eliminate this steady state error. So we increase I gain until we get short enough convergence time. Then finally we switch to degain. So we increase the degain to decrease the overshoot and to make the system stable. And regarding the UART communication I'm using, I use QBMix file, QBMix software to configure it. So I choose asynchronous mode, but I keep all the parameters by default. I haven't changed anything here. But I enabled DMA, so I'm using a normal mode. I increment memory, and data weights is 1 byte. And also I use this function, receive to idle. The main difference of this function from the conventional receive function is that it waits until the end of the transaction. So instead of getting like a specific number of bytes, you can get the whole message. I think it's a really good thing. But also you need to specify the maximum number of bytes you can get. I usually set really high value that I never achieve. So this callback function is invoked when you get the whole message. So in my case, I have numbers, but what I receive is ASCII values of digits of these numbers. So I subtract 48 from these ASCII values to extract digits. Then I use this while loop to compute these numbers. So until we have the empty space, I just multiply this value by 10. So at the end I get P gain. Then I have I gain. So I do a similar approach. Then I have D gain. Then I wait the next message. And from the computer side, I have this software PID. So here you just choose serial, you specify speed. So in my case, I have this speed by default, comport 3, and inside of terminal you just choose force on, you open, and you can send numbers, any message you want to the microcontroller. And regarding this code, I have a separate video where I showed how to implement PID, and all the information about the hardware I'm using, about the code itself, you can get from the description. And if you like this video, please subscribe and press the like button. It will help me a lot to provide you with interesting content and more useful information. So see you in the next video.